In our lesson today, we're going to have an activity that looks at the areas of two different squares. I've got a square here that's on the left side and a square here that's on the right side. Both squares have side lengths of a plus b, but the squares have been divided up differently. Okay, so to get each edge of this square, I would have to add a and b together. And same thing over here with this square. To get the length of each edge, I'm going to have to add a and b together. So the side length of each square is going to be a plus b. All right, and in the first question, they ask us, why do the squares have the same area? Okay, and we can easily say that the areas are the same. The areas are the same because the side lengths are the same. The areas are the same because the side lengths are the same. Remember that for a square, in order to find the area, we have to do base times height. And for each of these squares, all right, to get the base value, we have to add a and b together. So it's some quantity a plus b. And the same thing for the height. I would have to add the side length of a plus b together. So that is also some quantity a plus b. Okay, and again, that's the same for both of the squares. The side lengths are a plus b. So to find the area of this square, I can simply rewrite that as the quantity a plus b squared, since this is repeated multiplication. All right, this a plus b times this a plus b is just a plus b squared. So again, the areas are the same because the side lengths are the same. All right, the second thing that they ask us to do, it says, for each square, write the areas of the smaller shapes inside of them in terms of the variables a, b, and c. So if we look back at our two original squares, notice how they've been divided up. Okay, over here, I have a small square, a bit of a larger square, and then two rectangles. But for this square, I've broken it up where I have 1, 2, 3, 4 triangles. And then here, I actually have a larger square. All right, so let's find the area of each of the smaller figures inside of these squares. So we'll start on the left, and we'll start with this small square here. To find the area of a square, we do base times height. The base is a, the height is a times a is a squared. For this rectangle, to find the area of a rectangle, we do base times height. Well, the base is a, or b rather, and the height is a, so b times a is the same as a times b, which is the area of that rectangle, AB. For this rectangle, base is a, height is b, a times b again is AB, so these rectangles have the same area. And we have another square here that measures b by b times b is b squared. All right, so those are the areas of the four smaller shapes inside of this square. For the square on the right, again, I have 1, 2, 3, 4 rectangles. Each of these rectangles has dimensions of a by b, a by b, a by b, a by b. To find the area of a triangle, remember you do half of base times height. So in each example, we're going to have to do 1/2 of a times b in order to get the area. So that's the area of this triangle, and that's the area of this triangle, 1/2 a times b. Same thing for this triangle, 1/2 a times b. And the same thing for this triangle, 1/2 a times b. So those four triangles have the same area. And again, we have a c by c rectangle. So since the values are the same, it's actually going to be a square. And these are right angles. Okay, so I know I'm working with a square since the sides are the same. C times c, the area of this square is going to be c squared. All right, let's check out what they want us to do next. In the third part, it says the combined area of the four triangles in the second square is equal to the area of what in the first square? All right, so if we take a look up here, we have four triangles. Each one of them had an area of 1/2 AB. So what I can do down here is I can take that area, 1/2 AB, and I can multiply that by 4. And 4 times 1/2 is 2, so this is just 2AB. So I'm looking for something in the first square rather, that has an area of 2AB. Well, if I look at my first square, well, I see an AB here, and I see an AB here. And if I were to combine those, all right, AB plus AB, well, there's a coefficient of 1 in front of each of those. 1AB plus 1AB is 2AB. So those are equal to each other. So where did those come from? Well, again, the 4 triangles on the second square, those combined made 2AB, as did these 2 rectangles from the first square. So we can say that the 4 triangles in the second square, the 4 triangles in square number 2, have the same area, as the 2 rectangles in square number 1. All right, the 4 triangles in square number 2 have the same area as the 2 rectangles in square number 1. And I can even prove that if I go back up and look at square number 1. If I look at these 2 rectangles here, if I draw in a diagonal in both of those, now instead of having 2 rectangles, I again have 1, 2, 3, 4 triangles. Each of them have an area of 1/2 AB, which matches the 4 triangles over here in square number 2. All right, so the 4 triangles in square number 2 had the same area as the 2 rectangles in square number 1. All right, and the last thing that I want to do here, it says, based on your answer from number 3, so what we just did here, what must the sum of the areas of the 2 small squares in the first square be equal to in the second square? Okay, so if I look back here, all right, I already knew that these 2 rectangles had the same areas as the 4 triangles in this square. So if I were to take these rectangles out of square number 1, I would have to take away these 4 triangles in square number 2. And so what that leaves us with in square 1, we have this a squared and this b squared. So if I were to add these areas together, that has to be equal to what's left in square number 2, which was this area of the square of c squared. Okay, so based on example number 3, the sum of the areas of the 2 small squares, well, that was a squared plus b squared, that has to be equal to c squared, which was the area of the bigger square in square number 2. Okay, so we have this equation now that says a squared plus b squared equals c squared, and hopefully that's an equation that seems familiar to you. In our next picture, they ask us to calculate the area of each square in the picture below. Okay, so I can see that I have 3 squares in this picture, and let's see if we can find the area of each of those. All right, so looking at this square down here first, well, I see that this edge has been labeled as 4 units, and if it's a square, that means all of the sides have to be 4 units. And to find the area of this square, we again do base times height. So if the base is 4 and the height is 4, that means that the area is going to be 16 square units. All All right, for this square here, I can see that this edge has been labeled as 3 units, which means that all of the sides are 3 units. Base times height for this square, 3 times 3, means that the area is going to be 9 square units. And for this square, I can see that this edge has been labeled as 5, which means that all the sides are 5 units. So base times height, 5 times 5, means that this is an area of 25 square units. All right, and underneath in question 6, it asks, how does this relate to the equation that we found in the previous example? All right, well, if we bring in that previous example down here, we said that the sum of the areas of the two small squares, a squared plus b squared, was equal to the sum, or the area of the larger square. And if we take a look at the numbers that we just found here, if I take the areas of 16 and 9 and add them together, 16 plus 9 is 25, which is the area of the larger square. All right, so how does it relate to the equation that we saw before? Well, we can say the sum of the areas of the two small squares is equal to the area of the large square. All right, the sum of the area of the two small squares is equal to the area of the large square. We had 9 and 16 as the areas of the small squares. 9 plus 16 is equal to 25, which was the area of the larger square. Okay, and again, another way that we can write 9, well, that's just 3 squared, and we had to do that because up here, each side of this square was 3. 3 by 3, 3 squared. All right. 16 is better known as 4 squared, which again is 4 times 4. And that's equal to 25, which is the same as 5 squared, or 5 times 5. So 9 plus 16 equals 25 could also be said as 3 squared plus 4 squared equals 5 squared. All right, so looking at the bottom here, it says, notice that 3, 4, and 5 represent the side lengths of the right triangle as well. We can look at the picture and notice here that we have a right triangle whose side lengths are 3, 4, and 5 units. Okay, well, in a right triangle, the smaller sides are called the legs. In this case, that's the 3 and the 4. All right, the 3 and the 4 in this example are the legs. They're the two small sides of the right triangle. While the biggest side is called the hypotenuse. All right, the largest side of the right triangle, in this case, the 5, that is known as the hypotenuse. In any right triangle, the sum of the squares of the legs is equal to the square of the hypotenuse, which we can see right here. The sum of the squares of the legs, 3 squared plus 4 squared, becomes 9 plus 16. All right, that's equal to the square of the hypotenuse, 5 squared, which is 25. This is known as the Pythagorean theorem, and the Pythagorean theorem is represented using the following equation: a squared plus b squared equals c squared, where again, a and b, the smaller sides, are called the legs, while c, the largest side, is known as the hypotenuse. All right, the hypotenuse is the largest side, and if we look at our picture of the right triangle again, the hypotenuse, the longest side, the biggest side, is always located across from the biggest angle, which in this case has to be the right angle. The right angle is the biggest angle in the triangle. Across from the biggest angle is the biggest side, which again we call the hypotenuse. So now that we understand what the Pythagorean theorem represents, a squared plus b squared equals c squared, a squared and b squared are the squares of the legs, which are the smallest side of the right triangle, and c squared is the square of the hypotenuse, the biggest side of the right triangle, we can use the Pythagorean theorem to find the missing side length for any right triangle. So let's take a look at these two pictures underneath. All right, notice that this is the unknown side on the triangle, and this side is located across from the right angle in both cases, which means that the missing side is the biggest side, better known as the hypotenuse. We're looking for the hypotenuse in each one of these triangles. In order to find the hypotenuse, let's start with the Pythagorean theorem. A squared plus b squared equals c squared. All right, the two smaller sides are the legs, which were the values of a and b. It doesn't matter if these, which one is a and which one is b, they're interchangeable. So I'm going to start off by writing 12 squared plus 9 squared equals c squared, which again is the hypotenuse squared, which is the value that I'm looking for. Knowing my perfect squares here, 12 squared is 144, and 9 squared is 81, so 144 plus 81 equals c squared. And since these are on the same side, I can add them together. 144 plus 81 makes 225 equals c squared. So that's the value of the hypotenuse squared. Well, I just want the hypotenuse. In order to get the value of c, I'm going to have to do the square root of c squared. Whatever I do on one side of an equation, I need to do on the other side, so I'm going to do the square root of 225 as well. The square root of c squared is just c, and 225 is a perfect square, so when I do the square root of 225, I'm going to get 15. So c equals 15, meaning that the longest side, the hypotenuse here, is going to be 15 inches. All right, let's find the hypotenuse of this right triangle. Again, starting with the Pythagorean theorem, a squared plus b squared equals c squared. Again, the legs, the two smaller sides are given, 10 and 8, and again, they're interchangeable, so I can have 8 squared plus 10 squared equals my hypotenuse squared. 8 squared is 64, 10 squared is 100, equals c squared, and I can combine 164 to make 164 equals c squared. So since I now know the hypotenuse squared, to find the hypotenuse, I'm going to take the square root, and I'll do it on the left side as well. The square root of c squared is just c. Now, the square root of 164, well, 164 is not a perfect square like 225 was. So that means when I do this square root, I'm going to get an irrational number. Up here, they said, round your answer to the nearest tenth if your answer is irrational. So we're going to go ahead and use our calculator to figure out what the square root of 164 is. So here's my calculator, and your calculator might be a little different, so the buttons might be a little bit different. But what I'm going to do, I'm going to type in my 164, and then I'm going to find the square root of that, and there we are. I'm going to write out all of those numbers, 12 and 806248447. Okay, and I know that that number makes sense because if I know my perfect squares, the first perfect square less than 164 is 144, and the first perfect square more than 164 is 169. And if I take those square roots, the square root of 144 is 12, and the square root of 169 is 13. So I know that this square root has to be in between 12 and 13, and it is. Okay, let's now round our answer to the nearest tenth. C, the hypotenuse, is going to be approximately, well, that 0 in the hundredths place isn't enough to round us up. C is about 12 and 8/10, and the units are centimeters. So that's the approximate hypotenuse for this right triangle. In our next set of pictures, again, I've got two right triangles where one side is missing. All right, I'm missing this side on this right triangle, this side on this right triangle. Notice in both of these right triangles, across from the right angle is the hypotenuse. So I know the hypotenuse in each of these which means I must be missing one of the legs. We can still find the measure of the legs by using the Pythagorean theorem. So let's start over here. A squared plus b squared equals c squared. All right, now one of the legs is given. All right, 8 is one of the legs. It doesn't matter if you call that a or b. It's entirely up to you. I'll say that 8 squared plus my unknown leg here, b squared, equals the hypotenuse squared. So I'm going to substitute in 17 as the value of c. Let's go ahead and evaluate the exponents. 8 squared is 64, plus, I don't know what b squared is, but 17 squared I know is 289. All right, well, I've got to get my variable term b squared all by itself, which means I should subtract 64 on each side. And when I do that, b squared is going to be equal to 225. That's the leg squared. To get the leg, all I'm going to have to do is take the square root and make sure that you do it on both sides. The square root of b squared is b, and the square root of 225, we saw that earlier, that's a perfect square. The square root of 225 is 15. So this missing leg here is going to be 15 feet. All right, let's see if we can find the missing leg in this picture. Once again, we'll start with a squared plus b squared equals c squared. Here our known leg is 14. Let's plug it in for b this time since we didn't do that before. A squared plus 14 squared equals the hypotenuse, which is 20 squared. All right, well, we're going to keep a squared. 14 squared is 196, and 20 squared is 400. And we have to get this a squared alone, our variable term, so we'll subtract 196 on each side, leaving us with a squared on the left. 400 minus 196 is 204 on the right. So that's the leg squared. We need to do the square root now on each side to get the value of the leg. The square root of a squared is a. Now, the square root of 204, well, 204 again is not a perfect square. It's going to be an irrational number. And if I could think about my perfect squares again, the first perfect square less than 204 is 196. The first perfect square more than 204 is 225. So if I take their square roots, I know I'm going to be between 14 and 15. So if we pull out our calculator again, we're going to type in the square root of 204. 204, take the square root, and there's a number that looks good to me, 14 and 28285686. And then once again, we're going to round this to the nearest tenth since it's an irrational number. A is approximately 14, and this time that 8 is enough to bump up our 2 in the tenths place to a 3. So this missing leg here is going to be approximately 14 3/10 feet. In the next example, they want us to draw a diagonal line in each picture and then calculate the length of the line. And once again, if our answer is irrational, this time we're going to round it to the nearest hundredth. All right, so for each of our pictures, let's start by drawing in a diagonal line. I can draw in that diagonal like that in the square. And for the rectangle, maybe I'll draw in that diagonal line there. That looks good. All right, so those are the diagonals that I've drawn in. And notice what the diagonal does to each picture. Instead of having a square now, what I have is 2 right triangles. All right, and same thing with the rectangle. Instead of having 1 rectangle, now I have 2 right triangles. All right, and what I want to do is try to figure out what the length of the diagonal is. If you look at each picture, notice that the diagonal is located across from the right angle. All right, the diagonal is across from the right angle, which means that the diagonal must represent the hypotenuse of each right triangle. So let's start over here on the left, all right? In order to find the length of this diagonal, which is the hypotenuse of a right triangle, I'm going to use the Pythagorean theorem, a squared plus b squared equals c squared. Okay, and if I think about this right triangle here, I know that this is 5 inches, and I know that this is also 5 inches, and those are the legs. So I'm going to say 5 squared plus 5 squared equals the hypotenuse squared, which again, the hypotenuse is my diagonal. 5 squared is 25, so I'm going to have 25 plus 25 equals c squared. And when you add 25 with 25, that makes 50 equals c squared. To get the value of just c, the hypotenuse, I'm going to need to do the square root on each side. The square root of c squared is c. 50 is not a perfect square, but I know it's going to be very close to the square root of 49, which is a perfect square. The square root of 49 is 7. So square root of 50 should be very, very close to 7. Let's punch it into our calculator. We want the square root of 50. And yeah, that makes sense. Very, very close to 7. Let's write out all those digits. 7 and 0, 7, 1, 0, 6, 7, 8, 1, 2. Now they want us to round it to the nearest hundredth since this was irrational. So c, the hypotenuse, is going to be approximately, well, this 1 in the thousandths place is not enough to bump us up, so we'll keep it at 7 and 7 hundredths. And the units, 7 and 7 hundredths inches, is the approximate length of this diagonal. Same process for the rectangle. To find the length of the diagonal, use the Pythagorean theorem, a squared plus b squared equals c squared. 3 and 7 are the legs of this right triangle here, so I'll substitute those in. 3 squared plus 7 squared equals c squared, the diagonal squared. 3 squared is 9, 7 squared is 49, equals c squared. 9 plus 49 is 58, equals c squared. So once again, to get just the value of c, the hypotenuse, I need to do the square root, and I better do that on both sides. 58 is not a perfect square, so I know when I do the square root, it's irrational, and let's punch that into our calculator. The square root of 58, 7 and 615, 773, 106. And now let's round it to the nearest hundredth. C is approximately, well, that 5 is enough to bump us up. 7 and 62 hundredths. 7 and 62 hundredths inches is the approximate length of that diagonal.